Hello students. So in this class we'll be talking about phase space. Phase space is actually a combined position and momentum space. It is also called gamma space, where combined position and momentum space is called a phase space. So that means if we have three components of position and three components of momentum, so a point in a phase space, it will have six components: 3 for position and 3 for momentum. And instead of calling it as a 6 component, what we do, we hypothetically we divide the phase space into 6 dimensional cells. So each point is actually, since it has got 6 dimensions, so each point corresponds to a 6-dimensional cell. So have a 6-dimensional cell cannot exist, but hypothetically it is considered that. And this cell, this 6-dimensional cell, will have 6 sides, and these 6 sides will be your dx, dy, dz, and dpx, dpy, and dpz. Okay, so x, y, and z for the position, and dpx, dpy, dpz for the momentum. So naturally, the volume of the cell, we call it as the volume, d tau will be dx, dy, dz, dpx, dpy, and dpz. This will be the volume. Now, according to the uncertainty principle, dx, dpx should be greater than or equal to the Planck's constant, and so it is for dy, dpy, and dz, dpz. Therefore, the volume which is actually dx dy dz into dpx dy dpz is actually should be greater than or equal to h cube. And also we can say that the minimum volume of the phase space cell is h cube. So a particle in a phase space cannot be considered exactly located at a point, but somewhere in the phase cell. So since it is following the 3-dimensional Heisenberg principle, so we have a phase cell here. So particle cannot be said that where it is exactly, but instead of saying that, we say that it is inside a cell whose volume is of the order of h cube. So that we can say. So particle located inside cell, which is not exact location. Okay. Now, microstate, next we come to the microstate. The microstate of a particle can be specified by the 3 position x, y, z and the 3 moment of the coordinates. So we have a volume, as we have said, that it is equal to dx, dy, dz, dpx, dpy and dpz. So this is for one single cell. So for the total phase space, total volume of phase space, there will be an integration, 6 integrations, 3 for the position and 3 for the momentum, into dx, dy, dz, dpx, dpy, dpz, and this we consider v as equal to dx, dy and dz. So in the energy range 0 to E, so what we have is if we create a sphere, a momentum space with the dimension px, vy and pz, and so the volume of the sphere will be 4/3 pi p cube, or we can call it p max cube, and so we can write this part, the integration of the momentum part is dpx, dpy and dpz integration as equal to the volume of the space created by px, vy and pz, which is 4/3 pi p max cube. Now since E is equal to p square by 2m, so this p max square is equal to px square plus py square plus pz square, that is equal to 2m into E. So instead of writing p max square, what we can write is integration dpx, dpy and dpz is equal to 4/3 by 2m E to the power 3 by 2. So the total volume, we started with the total volume of space, total gamma space volume is equal to V multiplied by this term 4/3 by 2m me divided by 3/2. And now and so how will you find the number of phase space? So here you know that the minimum volume of the dimensions of the cells is h cube. So if we could divide the total volume by h cube, we will get the total number of phase space, total number of phase cells in the phase space. So use a different color. Say number of phase cells in gamma space is equal to V, the same term, 4/3 by 2m e to the power 3/2 divided by h cube. This will give us the number of phase cells. Now the next concept is of an ensemble or ensemble or whatever we call it. An ensemble is actually each phase point of a separated system with the same macroscopic properties but different microscopic state. It's called an ensemble. So each phase point can be considered as a separate system with the same macroscopic properties but different microscopic state. Now this large number of such similar non-interacting independent systems form a group. So a large number of such non-interacting independent systems they form a group, and that group is basically called the ensemble. Now we have basically three types of ensembles. We have a microcanonical ensemble, we have a canonical ensemble, and we have a grand canonical ensemble. So these are the three different types of ensemble. Coming to the microcanonical ensemble. these are a collection of independent assemblies having the same energy. So they are characterized by same energy, volume, and number of particles. Whereas a canonical ensemble has same temperature, volume, and number of particles. And lastly, the grand canonical ensemble this has same and grand exchange of energy as well as particles take place with heat reservoir. So you can write exchange of energy as well as the particles, they take place with the heat reservoir. And this canonical ensemble again, this canonical ensemble, this can again, it can exchange energy, exchange E, but not N. Energy can be exchanged, but not the number of particles. Whereas in a grand canonical ensemble, you can exchange both E and N, and whereas in a microcanonical ensemble, you cannot neither exchange E nor N. So, no exchange in the case of microcanonical, exchange of only E in the case of canonical, and exchange of both E and N in grand canonical. That is the difference between these three ensembles.